about some of the opportunities and challenges in next generation photovoltaics, focusing on the balance of systems. I could talk about this for weeks on end, so this is just a select few topics that are in our current research portfolio at Texas A&M University. And yes, I am competing with NASCAR to see who could get the most stickers and logos on their dashboard here. Okay, let's see if we could advance. Okay, so for those of you who don't know me, I've been working in the PV industry since 2002, both in a startup company, entrepreneurial activities, as well as in a university, in graduate school, and then as a faculty at Texas A&M. So a lot of my work here is focused on industry responsiveness and solving practical real-world problems with commercializable technologies. You can see that a lot of what I do is also on the standards development and reduction to practice side, as well as the university research. So when we talk about the balance of systems, these are really cost drivers. So beyond the solar cells, whoop, why is this advancing by itself? Okay, so beyond the cost of the solar cells, there are significant additional cost drivers. And some of these include issues regarding service life, so replacement and operating and maintenance costs for over 30-year service life of the solar panels and the energy system. Labor cost, both the installation as well as service, well, they just continue to rise. So the amount that it costs you at day 0 to install versus how much it costs to repair on a per hour basis, if a failure occurs, continues to increase. Also, there's uncertainty in political climates, feed-in tariffs, rebates, incentives. These are all bankability concerns that ultimately add cost to photovoltaic systems. Emerging and changing requirements such as California Rule 21, I got that typoed there. That's a completely different thing that I wrote in there. It's California Rule 21 that's adding additional requirements to the performance of the systems. There's the so-called smart inverter where PV has to do more than just generate real power. So what we really need is total system thinking. So we need to address the lifetime costs, that's cradle to grave, not just the first cost, and do this in a techno-economic optimization that really gets the right performance at the right price point, which may end up being application or technology specific optimization. Looking at hyper-customization for individual preferences as we penetrate into a more of a resi or residential market space, as well as looking at manufacturing, supply chain, go-to-market channels, and all those usual things that we think about once we get technology out of the research lab and into the marketplace. So what is balance of system? Well, balance of system is labor intensive. And if you've never been to College Station, you'll recognize the former view of Kyle Field. It's now changed a little bit. So cinder blocks and unglamorous nuts, bolts, and metal is what the balance of system is. Requires advanced training in some cases, and if you live in a union state, that could be up to $80 an hour to pull DC wiring through conduits. I think I picked the wrong job. Thousands of parts to fail and install. We see lots of opportunities here of unsupported wires that are dangling in the breeze that could chafe and fail with arcing. Lots of nuts and bolts, and basically a lot of redundancy in the system that need not there if we really do a holistic ground-up systems design. Plus, there's a whole lot of other things that people don't see. This is the inverters and the electronics that go inside the electrical rooms that need to be installed, configured, and commissioned. Not to mention susceptible of environmental conditions. So this is what the solar panels look like when they're just installed or operating properly. And after a day, a normal day in Qatar, you see that we call that dust or organic deposits, the euphemism. All of these have very negative effects on the performance of the PV. There's also non-hardware balance of systems issues, systems integration, the white-collar engineering design, customer acquisition and management, supply chain and logistics, financing, project development, EPCs, the design work, permitting, interconnection, and inspection. All of these add costs beyond the cells to a photovoltaic energy system. So I wanted to focus on this presentation on a selection, or vignettes, if you will, of some currently funded research projects. And I noticed that the vast majority of my students are on the call, so hopefully you recognize something that you're working on in this list. So we'll start off with technology that we call solar ags. So the idea here is automating and hyper-customizing residential PV design and lead generation. So let's go ahead and see how this works. So meet Jack and Jill homeowner. It's Saturday morning. They're talking about CNN that they heard last night, something about solar becoming more popular. Now they're environmentally friendly, and they live in an area where there's other environmentally friendly people, but they've had problems doing home repair jobs. They don't want to break the bank on anything. They're especially afraid of this guy showing up trying to sell them something, or some power purchasing contract that they just don't understand what's going on. So what are they to do? How will that solar array look like on their house? How will it perform on their house? How much will it cost Jack and Jill? And how can Jack and Jill trust the installer? Legitimate questions for someone thinking to go solar. On the other side, meet Hank the installer. He really takes pride in his job, has taken the necessary time and investment to get the proper certifications, but seems to be spending a lot of time driving around town, chasing down leads for people who are really just window shopping, and claim to have no money when it comes time to actually purchase something. Plus, the rules and regulations have him doing more paperwork than actual installations. And in the end, he's just really frustrated with the industry that he loves. So what's the problem? The problem is the cost of developing a customer. So leads cost anywhere between $35 and $50, with a typical conversion rate of 5 to 20%. So there's a lot of time and effort going into developing a customer. NREL estimates that it's $2,400 for a 5 kilowatt resi system. So we could break that down into 8 cents per watt for system design and 40 cents per watt for all the other acquisition costs. So this is significant when you think of some of the DOE's targets of $1 per watt for solar or less. So these are significant numbers. So what have we come up with? Solar ags. So the concept here is let's use technology to address this problem. So the homeowner interfaces with solar ags, our smartphone app, that does all of the automatic design, interfaces with the installer, interfaces with the AHJ, and provides a fully qualified lead who's ready to buy, a full design package that's ready to install, as well as full local jurisdiction permitting and inspection. And it even helps schedule the installation. So all completed with just a few minutes. So how does it work? Well, the first thing we need to know is where you're located. So it locates the user, takes an interview of the user to find out what their appetite is for how much they'd like to spend on it, what their energy usage is, some basic stuff that most homeowners could find off their utility bill or bank account. And then takes a picture of this house, and all that goes to a back-end algorithm where it's processed. So in the back end, we go through and do a series of image processing. And basically what we're looking at here is being able to automatically design the PV array for their house. We're going to slow that down a little bit because it went by fairly quickly. So we take a picture of their house. We're going to isolate the roof from the background. We're going to look for extremum points, the corners, and any other features on it. This gives us the ability to lay down a wire mesh and figure out exactly the usable space that we have to work with. Then we start applying our optimization algorithms that computes the mechanical properties, electrical properties, and also starts to predict the different performance aspects of the system. So this allows for multiple different combinations of technologies and system configurations. So we could explore on-grid, off-grid, thin film, poly, mono, whatever. It's all possible because this is all done in a cloud computing environment with no user in the loop. We've also got some other secret sauce that I can't tell you about now for roof penetrations and things like that. So when this back-end algorithm is all done, it returns to this smartphone app a picture of Jack and Jill's home with the solar on it. So this is not an artistic rendition. This is the actual house with the actual optimally designed solar array. You can even see on here the red parts are the keep-out regions due to shadowing that was automatically calculated. In many cases, there are more than one right answer, so Jack and Jill get to pick one that matches their budget or looks the most aesthetically pleasing. They could choose their favorite installer, or actually, in the future, perhaps this might be allowed one day where it becomes a do-it-yourself project. So on the soft cost side, in addition to lead generation, we're also removing a whole lot of the bureaucratic red tape. In fact, if we look at what's going on there, or what has already occurred in countries like Germany, how they can move from months to weeks to just a few hours of a solar installation is by eliminating all of this bureaucratic red tape that the installer and user needs to move through. So we could do this all with the technology in the smartphone app. What we're really looking at is on the soft cost breakdown. Basically, 2/3 of the soft cost can be addressed with appropriate use of technology. Again, not a single solar cell here, but looking at the other costs in the systems and how can we address that with technology. Wanted to look at a different research project now, novel photovoltaic arrays. This technology has actually already been commercialized through one of our R&D partners. So if we start by thinking about what's inside a traditional solar box, we have lots of parts. Whether it's a smart inverter or dumb tubing, we also have manual labor that's required, additional tools that are needed, skyjack, sky lifts, just a whole lot of stuff that we need. Well, suppose we didn't need all this balance of system hardware. Suppose we could use an existing infrastructure right as that solar array. So suppose we develop a new concept for PV, and many of my students will have actually participated in our pilot demos of this. Suppose we could use our football stadium as a 9-month-a-year solar array, and we could simply install the solar panels directly to the stadium seating. So no racking, none of the other equipment that we normally associate with the mechanical attachments. So through our R&D development partner, we have a patent that was issued in May 2014, and our R&D partner is actually actively commercializing this already. If you take a look at it, this is sort of what it looks like up close. It's enabled by quite a bit of technology. So AC PV modules means that we have no DC wiring, and the modules make AC power directly that are easily strung together with quick connect wires. So the secret sauce, if you will, here is the clamping mechanism. Now, this is an early prototype version. It's since been refined, but basically allows a very rapid installation. In fact, a 4 kilowatt system was installed in something like 35 minutes. So that's unheard of in the industry. So what's the value proposition of something like this? Repurposing existing infrastructure. So we could leverage CapEx costs that are just sunk. The racking in this case could be the stadium bleachers for this application. It's already secured. We already have the concrete footings. We already have the metal superstructure. And in most stadiums, the electrical service is already installed for when they have food concessions. The AC PV module means that the ground wire is all taken care of, and it's simple plug-and-play wiring. It also means that the system could be expanded to suit a growing budget or sizing options. We're not limited to the conventional system design of doing a DC array. Now, of course, we might be able to appreciate that this has applications well beyond just a football stadium, but military applications where the PV can be mounted. In fact, if you look at the Army and the Marines, they had done a number of prototype tests, and they found that everything else worked great except the PV mounting. They couldn't figure out how to mount the PV panels, so they literally made a berm of dirt and laid them against the dirt. Otherwise, the concept worked great. First responders, if we could mount solar panels directly to the exoskeleton for Texas Task Force 1, they have power built into their command shelter. Also, great applications for the developing world where we don't have the financing model to support all of the balance of systems, and we really need to be very judicious about where we put the money and put it where we're making the electricity and not all the rest of that. So a third project that we're working on is arc detection. And if we take a look at all of the opportunities in a solar array, there are many places where electrical hazards could occur. And if we look at some of the statistics, annually arc faults cause fire, shock hazards, and system failures, with over almost $30,000 worth of residential electrical fires per year, causing 360 deaths, 1,000 injuries, and nearly $1 billion in damage. These are staggering numbers. Now, any death is one too many, but when we look at the loss of fire, some of you may be familiar with a little incident up in New Jersey a few years ago, a 1.5 megawatt system. By the time the litigation is all said and done, will probably cost well over $200 million. Insurance companies could afford to pay out one settlement, but you better believe that their business model is going to differ. So the industry as a whole can't afford to keep having losses like this, and that's why arc fault detection is so important. Now, lots of people are looking at arc fault detection, and there's even products available out there. The conventional approach, the most popular approach, is to use a Fourier analysis method. Makes sense. So you decompose the arc signature into the frequency spectrum, and then you kind of look for some patterns. You apply perhaps some window mask detection to that, and if enough frequencies are above the limit, then you indicate a likelihood of arcing. Problem with this method is that although most engineers understand fast Fourier transform methods, they may not appreciate that this is exactly the wrong mathematical technique to use, because arcs are not Whiteson stationary, they're not periodic, they are random. And so Fourier analysis is predicated on periodic signals. So what we've done is taken a very fundamental approach and to say, how can we do this differently? So if we take a look at an example, and here's we're going to look at applying the fast Fourier transform technique. We have a 1,000 volt DC, 120 hertz power ripple. So this is a single phase system, and 2 kilohertz ripple. So that's the inverter switching. And if we look at the before the arc occurred and the after the arc occurred, and we look at what's going on in the FFT analysis, it's really next to impossible to detect any difference whatsoever. So for small amounts of arc noise compared to other signals that are purposely in the system, this FFT technique is just really not very well suited. And hence we get into empirical stories of researchers going out to Sandia and NREL and tuning the parameters of their FFT detection algorithms. The problem is that if the arc fault detection doesn't work very well, then we're jeopardizing the safety that we're building in. There's two issues of that. If it false detects, that's what we call nuisance tripping, and the inverters turn off and the array stops making electricity. And if it fails to detect, then we have a hazardous condition that occurs that we're unaware of. So the approach that we took was to look at wavelet decomposition as a technique, a mathematical technique that's more appropriately oriented for waveforms that have high frequency discontinuities in it. And so an example at the top of the slide here is depending on the exact level of the decomposition of our wavelet transform, and again, this is not enabling, so just a high level view, it's very easy to detect when the arc occurs. So we could use our wavelet transform as part of our arc detection. Another problem with the FFT analysis is basically to achieve good signal-to-noise ratio, we need to sample at high frequencies. And so on this plot, we're looking at the difference between a 1 megahertz sampling and a 100 kilohertz sampling. So the Nyquist sampling theorem aside, the higher the sampling frequency, the more expensive the hardware. So if we could sample at a lower frequency and have good detectability, then we're on the right path for a low-cost balance of systems design. So if we take a look at wavelet analysis, and again, the same kind of a comparison with a 1 megahertz versus 100 kilohertz, the difference is much less than on the FFT. So time domain, the arc is occurring. Now that's an interesting effect because let's go back to the FFT. So at the top of the FFT, the blue line, that's actually a time trace. And so we get to see visually that at about 4.5 seconds, the current drops a bit, and we have our arcing condition. The FFT analysis doesn't tell us the time at which the arc occurred. If we look at the wavelet analysis, the wavelet, the output is actually a time domain trace. And so we know exactly the time that the arc is occurring, and this gives us the ability to correlate what we detect and think to be an arc with other system events and disturbances. So again, increasing the likelihood that we are correctly identifying the arc and not just measuring some correlated noise to some other effect. So one of the challenges that we're facing on the UL Standards Committee is how do we go ahead and detect, rather test these detectors. So if you're not familiar with UL 1699B, this will be a requirement soon, and it will say something like, thou shall have arc fault detectors in your system. So it's imposing the additional cost of this. A major challenge is repeatedly trying to test the efficacy of these arc detectors. So waiting for an arc to occur is time consuming, and my students do want to graduate at some point. Trying to create one in the lab has many variables, and we could do things like in the lower left of the slide, a pull-apart method where we have electrodes that we separate and an arc is formed. But does that really measure real-world conditions? And plus, the arc characteristics are so dependent on external factors, the driving voltage, the load impedance. So it's really not a very sound way of doing reliable testing. So we came up with a test bed where we're actually using a replay technique coupled with a concept that we developed called the arc signal to noise ratio. And this basically allows us to mix the amount of power that we're putting in from the arc signature with the amount of power that we're putting in with other naturally occurring noise. This gives us a volume knob, if you will, of how much arc is present in the system, and so we could test the efficacy. So on the right-hand side of the slide, we've got examples of different arc signal to noise ratios, going from a 1 to 0.01. And we could use this to really test to see not only can the arc detector detect it, but at what levels of arcing. And all this without specifying capacitance, inductance, or resistance values that we need to do into a test setup. Very repeatable. And the holy grail is that we also want to look at arc flash. If you remember that earlier slide where we had the electrical wires that were unsupported swaying in the breeze, well, let's say that chafing starts to begin and we have that initial dielectric breakdown. Call it the spark plug effect. We know something bad could eventually happen because we have that initial dielectric breakdown. Some people might call that a partial discharge. If we could detect that, then we have the ability to go out and remediate the problem before it becomes a fire. This is important for both resi systems where you have combustible material directly adjacent to the solar panel, i.e. the roof, but it's also important for large-scale commercial applications where we might have grass or other natural environments that if we could detect the arc flash that is occurring, we could go out and fix that before it actually turns into a fire. So this is also an advantage for wavelet transform that the FFT algorithm just really is not very effective at. So I wanted to talk about another current research project, and that's non-planar PV systems. So if we think about what constitutes a module, and it's been historically defined by a silicon wafer. So it's flat, brittle, rigid. The new PV technologies are fundamentally different, and they no longer need to be flat and brittle and rigid. And in fact, we all see the research scientists in the lab holding a flexible cell. What happens to that flexible cell as it gets commercialized? It gets laminated to a piece of glass, and it becomes a rigid solar panel. So on the balance of systems side, how do we take better advantage of the capabilities of some of these new cell technologies and to actually be able to achieve things like solar tents and solar car canopies? The interesting thing is when I talk to the military, they've piloted, of course, these solar tents, and pretty much the universal feedback is they grossly underperform. And that's no surprise for those of us on the balance of systems side as to why they grossly underperform. If we also think about other concepts, they could be solar-powered shirts, so solar fabric. We've heard people talk about impregnating solar threads into materials for wearable electronics. Also looking at building integrated PV, where we can formally coat that PV material directly to, for example, a terracotta roof tile. But in order to be able to do this, we really need to understand the cell characteristics. And if we look at the different geometries, the terracotta roof tile might look a little bit like a mathematical model of a semi-cylinder. And in this case, there's really only 1 degree of freedom, because we can correlate moving in the z, the height, and the y-axis. And in this case, x is just as long as it needs to be, and there's no change there. So we have 1 degree of freedom for a roof tile. And we might have, say, 2 degrees of freedom on sort of this wavy blanket picture here. So as we're starting to think, how do we maximize the amount of power that we can harvest out of this? We need to understand the characteristics of the cell and need to understand the partial shading effects that are inherent into the geometry of how we're using those cells. So our novel power electronic circuitry is required, our novel control approach is required. Also enables the realization of PV skin that could be wrapped directly into an architecture. So in the bottom left of the slide, we have sort of a today's design where we take a aesthetic building and we put a support structure and put the PV on top of that. In the future, wouldn't it be nice to have aesthetically pleasing structures where you can't even tell that there's PV? And I guess the best PV is when you can't even tell it's there. The job of the architect shines through rather than the job of the PV engineer shining through. So some of the motivation behind non-planar PV work that we're doing. If we take a look at really what's going on here, it's the partial shading effect. Now industry is pretty much appreciated now that when we have any kind of gradients in a flat planar array, whether they be process gradients, thermal gradients, insulation gradients, we're going to have a difference in or a reduction in the amount of electricity generated. Basically, if we take a plot like this, so this is for a 2 kilowatt resi system where we have 15 total modules. If we have a partial shading due to a cloud, chimney, tree, what have you, the extent to which the array is shaded determines what our reduction in energy production is. So what we're plotting here is that in the center region here, we could get over 25% more energy out of the solar array just by being more intelligent about how we manage the modules. So we don't need to wait for a technology breakthrough in the PV cell efficiency. We can do this today and make a better utilization of our installed capacity. So lowering the levelized cost of energy. Also, last thing I want to talk about is the concept that we're working on for local area power and energy systems. So are there ways that we could take more of a systems engineering approach to how we integrate PV in the future? And so if we look at what's going on in the industry right now, we see it's always been this way, is that the utility imposes its regulations. And whether that's the utility imposing the regulations on the load characteristics and performance, or imposing those as flow-down requirements onto the inverter. And Rule 21 is certainly an example of that. If you're not familiar with that, it basically says that an inverter has to do more than just convert DC power into AC power. It has to do a whole lot of additional things. Having taken microinverters to market, all these other things require a lot of extra cost. So you want your inverter to communicate, great. So you need a chipset in there to communicate. You need a communication channel. You want your inverter to be able to generate reactive power instead of just real power. Great. So you need a more complicated topology that could support non-unity power factor. So all of these concerns, if we're not careful, will add additional cost to our photovoltaic array energy system. So are there ways that we can do this differently? Well, and in my research group, we're promoting this concept of a smart community microgrid. And the idea here is that we have behind the fence. So the term point of common coupling, this is where we connect into the utility grid. And if we put more things behind the point of common coupling, then we can control them differently, and we may be able to control that in a way so the utility doesn't even know we have them. So an example of this is that if we have a photovoltaic array, so whether that's a single large array for a community, so call that community solar, or if this is a plurality of smaller arrays, call it a residential solar model, they're all interfaced through a power electronics converter into a local distribution bus. We could add some central battery storage for this, also on that distribution bus, as well as manage the local loads. We could take this concept and program, if you will, the point of common coupling to have arbitrary behavior. So rather than having a volatility of energy generation where sometimes the system is supplying power to the utility and sometimes it's drawing power, we could actually program the interface profile in an arbitrary way. So we can make it look like our system is a dispatchable source, is a dispatchable load. We could do day ahead planning. We could do hour ahead planning. We really offer a lot of additional flexibility. So the idea here is that we're offering new tools for how we integrate PV. So we don't need to have the intelligence down at each power electronics interface that California Rule 21 is seeking, but we could have the interface and how we put together the community microgrid. So I think John said to try to keep it to half an hour, so I think I flew through that material quite quickly. But I did want to leave a little bit of time for some questions here. And one of the things that, of course, we'd like to talk about is that solar is only good as how we could evangelize about it. And so part of the teaching and research that we do is also the public outreach. So being able to disseminate, evangelize, if you will, the goodness of solar. And this was a non-technical project we did, put together a 30-second video clip that 2 football seasons ago, we saw 9 million TV viewers watching this when they tuned into a Texas A&M football game. So that's an excellent way to do the accidental learning, football fans learning about solar. Who would have thought? So with that, I think I'm going to bring this to a conclusion, and I think I've got about 15 minutes or so if anyone had any questions or if they wanted to go back on any of the slides and do a little bit of a deeper dive.
Okay, it doesn't look like we had anyone type in questions during the talk, but if you've got questions now that you're thinking of or would like to have addressed, please feel free to type them out, or if you've got your microphone connected, you can also go ahead and ask in the.
Does this mean that everyone's either my student and knows all this stuff already, or perhaps on the different side of the equation? Very well. Well, you know, I've let me. So, really, what we're trying to do here is the vision behind the balance of systems research is that if you think about who all of the stakeholders are in a photovoltaic energy system, we could really represent them by sort of this bubble diagram.
They didn't have any questions left to be answered.
You know, certainly in the 1970s. The research was focused on what it needed to be to get the solar cells, that technology moving. And as we strive now to make solar really a commoditized energy product instead of a niche early adopter product, we really need to be focusing on all of these stakeholders. And so I touched on a couple in the vignettes. You know, certainly the last one on how we connect into the utilities. You know, that's a very important one because we're going to see that as the level of penetration of solar continues to increase, this may be a limiting factor. We're starting to see that in some jurisdictions, the permits have either dwindled or dried up. We see that some reports coming out. So I saw one recently that people were sold. The paraphrasing the title, it said something like people were sold a bag of goods. That's not a good thing because it was claiming that all of this technology that was installed for the last 10 years is completely wrong and will need to be replaced to accommodate the Rule 21 kind of advanced feature sets. So as an industry, regardless of where we might find ourselves on this bubble diagram, I think that this is a good opportunity, it's a necessary opportunity through the UCRC to really articulate what we can do to meet these challenges, whether those challenges are perceived or real or contrived. That's not to belittle. There are some real challenges that are out there, and then there's also some challenges that are easily mitigated. And so as the Texas A&M research site joins with UT and Colorado State, this is a flavor of kind of what we're bringing into the mix there. Yeah, thank you, everyone. Kurt, thanks for your comment. Kurt was asking, do you see the on module? Ooh, okay, a couple of people, most of them are thinking. So, you know, Kurt, that's a really interesting question, because right now the cost structure, the incremental dollar per watt is still more for a microinverter kind of a concept. One of the things that we do is a lot of the value proposition calculations, and to see what does an on-module actually give you.
Well, I guess we'll just...
and it turns out that in sort of a ideal installation where we have acres and acres of perfectly flat modules with very little shading characteristics,
after 1 a.m.
it's tempted to say that it doesn't value very much, except for the cloud coverage aspect. So what we really need to do is when we apply the techno-economic optimization is try to figure out, is that going to be significant?
Who tuned in for the talk, joining us again.
So the on-module technology could come in a couple of ways. I noticed that you purposely left it vague. So if we're looking at a microinverter versus just the power maximizer. So for those of you who don't know the difference, the microinverter takes the direct DC from the solar cells and generates directly AC. Whereas a power optimizer does the maximum power point tracking and then produces a DC bus. So it's got the front end of the inverter without the inverter side of it. So that adds a lot less cost to the module, but also adds the most salient or important of the on-module characteristics. So we actually see that there's a pretty good uptick in folks doing the power maximizers. Whether it's like a solar edge kind of a concept, where it's a power maximizer that's designed to integrate with their inverter to really optimize at a system level. So I think that there's going to be plenty of opportunity going forward. One of the things, Kurt, also to answer that is, you know, every time I go to a module factory, one of the things that I notice is that there's a whole lot of cost involved in the binning process. Binning, B-I-N-N-I-N-G. And so where you take cells and you test the cells and you bin cells that are similarly performing, and you take a bin of similarly performing cells and you create a module out of that. And then you take then you test modules, you do a flash test on the module, you obtain its performance characteristics, and then you bin modules that are similarly performing and you ship them together to your installation. So all of this binning adds cost that's really not necessarily value added, right? It's adding cost because it's needed to get uniform IV characteristics, uniform module characteristics today, because that's what we know how to do. But if we look at the proliferation of an on-module power maximizer, suddenly it doesn't matter so much. So if today you had a solar array, and let's say over the course of the lifetime, some of the panels began to underperform. So whether there was a deleterious effect like a hailstorm or the neighbor's golf ball, or just, you know, typical aging gradients that would be associated with large-scale manufacturing, to go in and tactically replace one or two of those cells, one or two of those modules rather, you're introducing dissimilarity in that system. So by having on-module electronics, you could mitigate that concern. I got a thanks from Kurt, so I guess I answered his question. Got another question coming in here. Yes, Bauming. Yeah. You have a question? Anybody else has a question they'd like to ask as Bauming is typing in his? Feel free to as well. Okay, so Bauming's question is about renting as opposed to selling. So this gets into a whole, let's see, okay, he's still typing more. I'll let him finish. Okay, so how about that? So this really gets down to the soft cost side of financing and business deals. So we've actually seen that a major success in proliferating PV has been a power purchasing agreement. Basically, while they all differ a little bit, the basic tenet is that the PPA company owns all of the equipment, and then you enter into a contract to purchase electricity from that. A lot of people like this because then the cost of ownership is zero. It's sort of like, I guess, leasing your car instead of owning your car. So one of the things that affects the balance of systems costs for a power purchasing agreement is that someone needs to pay for the installation and removal of this equipment. And so to the extent at which systems could be skidded up, assembled off-site, and kind of delivered and deployed, that's something that would reduce that cost. So if you were talking about a commercial, like a C&I system, that might be 50 kilowatts to 100 kilowatts, for example, on top of your office building, being able to come in with a skyhook or extending a forklift and be able to just put something right onto the roof that's already pre-wired, pre-configured is a big advantage. And so to the extent at which technologies can support that is huge. This is it follows from the adage that the best reliability and the lowest cost structures in the factory. So the more we do out in the field at the installation site, the more it's going to cost and the less reliable it will be. So if you can make all your electrical connections and mechanical connections in the factory, you can test them, with very high confidence that this is a reliable system that you put together, and you also have your lowest labor rates in the factory. So if we see some of the, or a lot of the solar penetration doing a power purchasing agreement is very popular, and to the extent that going forward more of these systems become kitted up, I think we're going to see something like that. Okay, another question. Okay, so there's the question. They claim 20 years lifetime for PV systems. Is that true? No, but of course I have to backstep a little bit and say, well, if you're talking about a system, and for someone who is purchasing a system, they may not be interested in the granularity of what constitutes that system. While it is generally true that most manufacturers can create solar modules that will last 20 to 30 years, and this has been tested by NREL and Sandia time and time again, if we look at it as a turnkey system, there's plenty of other failure modes in that system. So for example, inverters. So a lot of my researchers are looking at power electronics. So if we have inverters, we have a number of different failure modes that are exacerbated by the environmental conditions. So hot weather exacerbates or accelerates the failure rate of inverters. Conditions on the AC power grid, whether it's lightning, surges, things like that, could cause accelerated failure on the inverters. So if we look at sort of where the industry is with the inverters, most inverters have anywhere from a 5 to 15 year warranty. So when we pair something that has a 5 to 15 year warranty with a module that has a 20 to 25 year warranty, we sort of immediately see that this is not really a system design approach. I thought you were going to ask me another question. Okay, so I have a question. So right now, the smartphone app is only considering planar PV. although that may or may not be on our developmental path. In order to keep this discussion sort of at an open level, purposely didn't get into anything that was proprietary or the secret sauce, kind of kept it at a fairly high level, hopefully generating interest in what we're doing, but without giving away all the secrets. Absolutely.